Yeah, so okay. So now so we should discuss what are algebraic groups or fine algebraic groups. So so also I want to make some small remark. So that we have introduced the notion of regular morphism. So if you are thinking about affine algebraic varieties, then you can reformulate this as follows. So if you have the morphism phi between varieties, then of course you have the notion of pullback. Yeah, so you have so if you have the function from k of y, it maps to the functions on x, yeah, via the pullback map, which is defined as simply as composition. Yeah, so given the function f from y into k, yeah, so you can consider the composition, so which we call the pullback of f, and which is simply defined by composing x with this regular function f, and this composition is just, it is called the pullback. Yeah? So so on the point x, it is defined as taking phi of x and applying f. And in terms, so you can speak about the, first of all, so you can speak about morphism as the map between topological spaces such that the pullback maps, so and of course here I have written this, so here we had notation for the set of regular functions. But in general, the pullback map, it maps functions to functions. Or, so if you start with regular functions, the pullback should map the regular functions, it maps to arbitrary, a priori arbitrary functions if you if the map you are taking is arbitrary. So the just phi is called regular, so phi is called regular if if you have the following, so if phi star just maps the set of regular functions on a y to the set of as to the subset in the set of regular functions on x.
It's second definition.
Yeah, it is second definition. The definition of regular map, equivalent of regular map. So and notice also, so given an algebra of functions, I want to recall how to reconstruct the variety itself. Yeah.
Is it true that if phi is surjection, then phi of a star is surjection?
If phi is surjection, then phi apostile is injection.
Okay.
Yeah.
I see.
Yeah, so and vice versa, if you have injection here, phi apostile is surjective map. So what I wanted to say here, so Yeah, so reconstructing a variety. Suppose, what is the aim of algebraic geometry? The aim of algebraic geometry is to solve geometric problems, but the main point why we want to make geometry algebraic is to have a geometric problem and then try to reformulate it purely without using geometry. So in purely in some terms as commutative algebra or something like that. And here, so we noticed that we started our studying X by taking embedding of X into a affine space. And then we constructed the set of regular functions. But then one can think, and what will happen if you forget about the set of, about this embedding, and remember only the set of regular functions. Yeah? So can you reconstruct the variety itself? Yeah, so, the answer is the following. So the set of points on X X correspond to maximal ideals here by Hilbert. Yeah.
You say we know like space set of functions. It means we know the ring structure or embedding to
ring structure. You do not have embedding of this. I mean, you have surjection of polynomial ring. In general, you have. In general, you have polynomials here. You restrict it. Yeah, so in general, you have this kind of picture. So you have collection of polynomials here, and they restrict to k of x.
So we still somehow know this bigger affine space.
Yeah. So you want, given this algebra, you want to, so notice that what else you know about this algebra? It comes from polynomial algebra, so it is finitely generated algebra over K. Yes, so it is finitely generated algebra. And so given finitely generated algebra, we want to recover, so given a finitely generated algebra, you want to recover information about X. And how to do it? So, for example, what is embedding? So, how to think of the coordinates of this just embedding if you have X. So, notice that you may think of xi, which are functions. So, the coordinates are functions on a affine space, of course. Yeah? And you have this inclusion, so you can restrict these functions to X. Yeah, so the restrictions of xi to X, in our more sophisticated terms, it is a pullback of the functions, pullback of coordinate functions of xi. So this becomes regular functions. And what do you know about these regular functions? These regular functions, so this is surjective map. So these regular functions, they generate X. Yeah, so the pullbacks of coordinates play a role of generators of X. Of k of x. So just if you have X and if you have collection of functions g1, gk, of course you can form the map to a affine space yeah, k-dimensional affine space by evaluating this collection of functions. So, how you can reconstruct some embedding when X is just embeds here as a closed subsets? It is simply the following. So take generators of the function of k of x, and let us denote it by y1, yn, yl, and you can map the corresponding polynomial ring x1, xl, yeah, so xn. You can map it to k of x such that this xi map precisely to the corresponding generators. And here you know that when you have the polynomial algebra, yeah, so you have the kernel here, which is ideal, yeah, so kernel of this evaluation map. And this is by Hilbert theorem on basis, this is finitely generated ideal. So finitely generated ideal. So it is generated by the collection of polynomials f1 of k, and you can use this collection of polynomials in order to define x as follows. So just embed x in affine space and dimensional affine space via the zeros of this system of polynomials.
Do you mean that
the kernel is precisely the functions should be precisely the function that vanish after restriction to x. Yeah, so and this map from x to affine space is in general given by this formula. You just take the values of the functions. Yeah? So starting with arbitrary collection of generators, you can map, starting with arbitrary collection of elements, you can map it, your variety to any the corresponding affine space. But if you start with generators, then you are mapping it isomorphically. So the only thing that, yeah, so you have the collection of polynomials, and you have that define x, which are generators of the kernel. And notice that the set of embeddings are in bijective set of closed embeddings of x into the affine space are in bijective correspondence with the choice of generators. Yeah?
I don't understand whether why I can be the same.
Yes, sure. This was the same, the second remark. Yeah, so let me formulate this that embeddings in AN are in correspondence closed embeddings as a affine variety of X are in correspondence of picking n generators of the algebra of k of x. And of course, if you have a union of one collection of generators and the other, you can take the union. Yes, so you can pick up so these are still generators. Yeah, so you can pick up here the collection of generators. You can pick up other collection of generators, and yeah, so this means that you have two surjective maps actually from K of y1, yk here. You have surjective map to Kx from K of z1, zl. And you also have the surjective map from y1, etc., yk, z1, zl. Yeah? But notice that geometrically this corresponds, so if you apply precisely this construction, yeah, so this will tell you the following, that x will map into a k here via the coordinates 1, y1, yk. It will map to yl, al via the coordinates z1, zl. And you may map this to the product, yeah, k times al via diagonal embedding. Yeah? So we are taking the coordinates y1, yk and z1, zl as the coordinates functions. And of course, yeah, so here you have projections, natural projections, which are consistent with this construction. Yeah? So you have, and for example, as it was your question, as I understand, what will happen if you take your generator twice? If you take your generator twice, then it is of course still system of equation, but you will increase the dimension of the vector space where you embed.
So idea is
yeah, so what?
So idea is if you have like some embedded variety in AN, you can like take
yeah, I'm listening.
functions which is like embed and then calculate xi and obtain your embedding back. It's kind of tautological.
Yes. Yeah. I mean, so that's a point that if you have this algebra functions, so then you tautological kind
So
of.
it's really just a thing that like if we will take a pullback of xi, it's a ith coordinate
Yes.
of our point after.
Yeah. Yeah.
Is it right that we take x in like in a fine space and then get it embedded in K?
You may think of this as, yeah, so for this construction, you may of course think of this as taking here, you have the map between AN, and so you have, but notice the following, so if in order to reconstruct this, so there is there are some ambiguities that occur here. So, for example, here you have the map that maps in order to fix this collection of equations, collection of functions. So these GIs are in the algebra of functions of X. In order to look at them the same generators as the functions on N, you have to lift them. Yeah? So you have to find the polynomials GI such that which are the, I shall denote them as the regular functions on AN, and such that the restrictions of GIs are precisely on X, are precisely this GI. And you may make this diagram commutative via here you are taking the map GI GN and GK, and here you may, given a point Y here, you may map it to G1, etc. GK.
Do you use it for a regular always possible to extend it to...
Yes, but not uniquely. Yeah. So you are so the regular functions on a fine variety is defined as the restriction of some polynomials, yeah, from a fine space. And but of course you notice that different embeddings give you different restrictions. But if you look at the images of these maps, they can become the same function here. So which is possible. I mean, as you are taking one generator twice. Yeah, so in your example that you are taking one generator twice, you are taking different coordinates, but on your variety they have the same value. Yeah? Okay. So this allows you, this allows you to reconstruct the morphisms. So given a morphism, you can reconstruct it by similar procedure. Yeah? So if you have morphism of a fine variety, I mean the following. So just so given a regular morphism, just given phi tilde, the map between kfy, kfx. So given homomorphism, you can reconstruct, we can reconstruct embeddings x in the affine space and y in the affine space, and such that you have this map between x and y. And this can be done as follows. So how you do it? So how to understand what is m and what is n here. So how to take this. So you are starting with this algebra. Yeah? So in order to reconstruct this embedding of y into am, you are picking generators. Yeah? So you are picking f, so let us pick y1, etc. y, yeah, so just z1, etc. zn. Well, g1, gn. You pick up gm, generators. So this, they map a point y into g1 of y, etc. gn of y. Yeah, so gm of y. So notice that after this, you may map these guys by the pullback here. Yeah, so you are mapping this to g1, etc. Phi star of g1. It is just homomorphism, yeah, between these algebras. You have a mapping between this g1, gm, and also, so these are just the set of elements. And you can simply extend them to generators. Yeah? So extend this set to generators of kfx. So this just give you additional collection of functions, phi 1, etc., phi n minus m. And so x is given via the following. So it is given by phi, so by phi 1 of x. So these are functions in kfx. Yeah. So the point x is mapped to f1 fn minus m of x, and to these pullbacks. Yeah. So just to g1 of phi of x, etc. to gm of phi of x. And you see that this map between an and am is nothing. It is what? It is projection. Yeah, so it is just you take these guys and project here. You just do nothing. Yeah, so you just take this function and you do nothing. It was needed only, so these functions were needed only for to formulate the notion of a regular map. So in fact, any map between affine varieties can be obtained as embedding an affine space and projection.
But what if these elements of C star, G1, Gm are dependent?
Independent?
No, dependent.
Dependent, it's nothing. I mean, you can take dependent element for the embeddings. I mean, you do not use it. I mean, you take the collection of elements. They can map even to 0. It's not bad. I mean, you just extend them to the set of generators. I mean, generator shouldn't be. It is just generator. So any element can be expressed as the polynomial on generators. It shouldn't be expressed uniquely. It's not basis.
Sometimes you don't need an extension. These elements are enough to generate.
Yes, sometimes it's enough.
You just put up a generator.
I mean, you put you take these elements, and if you need, you add the additional elements to generate. I mean, to have embedding here. But this is just to be consistent with the definition, I mean, of the map. Actually, what we really need is this collection of guys, yeah? So in order to reconstruct the mappings. Okay? So now I want to speak about algebraic groups a little bit. So algebraic groups. More generally, the idea is that you are just so we have defined the class of varieties. So for example, affine varieties. We have defined the class of maps. Yes, so this regular maps. The class of functions, regular functions. And the general setting is the following. So if you want to make a group out of something which is, and you want to add a notion algebraic, you just should have all the notions that are, the maps that are related with your group algebraic. And what maps do we have? So we have the product, so multiplication map, that can be viewed as the map from G1 to G, from the product of to the group G. And this, so mu of G1, G2. And this should be, notice that if you want to make the variety affine, yes, so you have, if you have two affine varieties, and x is embedded in its own an, and y is embedded in some am, so definitely you can embed x times y in am times an. And this allows you to say what is a product of affine varieties. So you just define it as a closed embedding. So note that if you look what is an algebra of functions, that algebra of, so let it be exercise, so that algebra of functions on yeah, so actually, so I think you should do this additional exercises, I mean, that just given through the lectures. So this algebra of functions on this product is just the tensor product of the algebras over K. Yeah? So, of course, I should explain what do I mean by this exercise. Yeah? So here you know how to embed X in a affine space. Yeah? So you know that it is generated by a collection of polynomials. Yeah? So F1, by the ideal I, F1, Fk. And you know that Y is defined by ideal J. So G1, etc., GL. So the thing here, yes, so the set of regular functions here, it is identified as the polynomial algebra x1, xn modular this ideal I, and just the algebra of so this algebra is identified with y1, ym over ideal J, and I claim that the algebra of functions of this product, so you're embedding this diagonally, so you have to define, first of all, the system of equation that gives you this embedding, and this tensor product should be just given as x1, etc., xn, y1, yn, modulo some ideal. Yeah, so, and you have to specify this ideal via this diagonal embedding, and so this component-wise embedding, and prove that this is consistent with taking the tensor product. So you have this product of G1, it should be a regular map. Also you have inverse, yeah, so you have inverse map. It is also should be regular map. And associativity condition, it is given in terms of commutative diagram. Yes, so in order to have associativity condition, you should be able to put brackets. Yeah, so to here on this first two terms, and here on the second terms. Yeah, so this is taking mu and mu like this, and here you are taking mu and mu like this, and associativity can be expressed as commutativity of this diagram. Yeah, so you apply mu here and mu here, so this diagram should be commutative. Yeah? So yeah, so this means that you are comparing this, yeah, so why I'm formulating this associativity is not automatic, because it is not set theoretic. I mean, in order to check associativity, you have to check that these maps are the same. Yeah, so this composition of these maps and these maps. Yeah, yeah. So I mean, yeah. So this just as for these maps, so this is composition of these maps. So this one and this one is the same. Yeah, and it is. So of course, if you are looking, if you are working in category of algebraically closed fields, you can check it element-wise. Otherwise, you should think of this as the equality of the maps. Yeah, so you are expressing these functions, these maps as in terms of regular functions, and you should have the equality on this corresponding regular function.
Do you mean that it is needed to check the algebraicity of associativity?
No, it's. I mean, if you have a group already, you have associativity. Yeah? But why I'm formulating this, because you should think of this as two maps two maps that this one is equal to this one, yeah, as two regular maps. But usually when you can do it element-wise, if you are working in the case of algebraically closed fields, our maps are in bijective, so the maps are defined on the collection of points. So for example, when it doesn't hold, so if you have real points, yeah, so the real points could be a quite small set. If you define the map on the set of real points, it could be different to maps which coincide on the set of real points. A priori could be different on the set of complex points as algebraic maps. So that's why I'm emphasizing this part. Yeah?
And if you want to formulate the example inverse map, shouldn't we fix
unit, yeah. Yeah, but unit is just it's a point. I mean, unit is just element of G. It is, it is automatic. Yeah. So here it is automatic. It's not. Of course, you can express the axiom of unit in terms of algebra. So what maps do we have? But if you are speaking about, so G is a group plus this kind of plus algebraicity, yeah. But I wanted to say that G is a group plus the algebraicity of these operations, and I wanted to explain here what is algebraicity.
I'm sorry. If you want to check associativeness,
Да.
Мы можем, ну, скажем, перейти к замыканию и там просто...
Да, конечно.
То есть это будет достаточно, да?
Ну, этого достаточно. Просто, почему я вот иногда оговариваюсь, потому что можно об этом говорить в более общем контексте. Вот, например, вот на прошлом курсе меня спрашивали про схемы очень часто люди. И вот, если вы хотите говорить о схемах, то есть, схемы, они приходят из того, что вы думаете, об этом скорее как об алгебре функций, как, вот из таких вещей. Разница между схемами и многообразиями — это в приведенности идеала или в неприведенности. И вот единственное, что просто, когда есть запрос о схемах, то нужно говорить в терминах отображений. Если мы говорим в терминах многообразия, вы можете... So if you are speaking about in terms of varieties, you can reformulate your statements in terms of points. Yeah? So you have the collection of points, you can have the mappings, and you check at the corresponding points. Yeah? So two maps coincide if they coincide on the collection of points. But if you want to state it in a more general context, you should speak about commutativity not element-wise, but of maps. Yes, so that the composition of two maps are the same maps. Yes, so that's why I'm speaking about. I try to formulate this in context that can be generalized easily. Yeah.
Can you repeat how did we define algebraic group?
So it is a group, just usual notion of group with additional operation, with additional structure. So the structure, this multiplication map should be the regular map of affine varieties. The inverse map should be a regular map of affine varieties, and you should have associativity, which can be formulated as the composition of these two maps. So the composition of this map and this map is equal to composition of this map and this.
If we have some GL of 1, which is like real number or
Yeah.
sample multiplication, is this inverse map regular?
Which one?
Like just non-zero numbers under multiplication is an
Yes, it is a regular. Yes, yes. Yeah.
So is inverse map regular?
Yes, on the set of all points without zero, yeah.
But it's not like
It's not written,
polynomial.
yeah, but the problem that, yeah, so what is your, just confusion? Yeah, so that, again, that this star, K star is sitting in K, yeah? And, but this is, yeah, but you shouldn't write down something, yeah, so you shouldn't write down the product between K star, yeah, in terms of embedding of this K, yeah, so you should write down this as embedding in 2x2 matrices, yeah?
2x2 matrices.
Yes, we did it here. I mean, we put GL, yes, sir. Yeah, so we put GLV into GLN into SLN plus 1. Yeah. So here you can take this, you can put these numbers as 2x2 matrices, but yeah, diagonal with only condition the determinant is 1. Yeah. So it's funny, of course, but yeah. So and it seems to be stupid, but now this map is precisely this map is regular. Yeah. So yeah, yeah, and this is just a product of T1 Z1 and T2 Z2, and of course, yeah. So here you have these conditions that is preserved. Of course, T1 is equal to T1 is equal to T2 inverse, and T1 is not equal to 0. But you shouldn't see it from. I mean, you see it from this embedding.
So we have restriction of polynomial with
Yeah.
matrix coefficients
Yeah.
because there is closed embedding and just.
Yeah. So here you have. So here is precisely the polynomial. So that maps the coordinates in the product. Yeah. So thank you for. This is very good question because it really illustrates. The problem. So now I want to usually what is yeah. So if you want to speak about subgroups, yeah. So just yeah. So you can do it in two ways. So you can speak about subgroup, which is just as a collection of elements, as an abstract subgroup, or you can speak about algebraic group. So just H is called algebraic subgroup, a subgroup, algebraic subgroup. If it is closed, a fine variety. So if it is closed, a fine variety in G. Variety in G. And here you have two options. Here you may think of H as the collection of elements with algebraic structure. So you may think that here it is two options of speaking about the group structure. One is saying that this diagram is commutative. Yeah. It's commutative. as the diagram of maps, or H is just a subgroup. Just H is a subgroup of G. So it is a group which is a subgroup, and so here which is a algebraic variety. Again, when you pass to algebraic closure, then you can. So when you pass to algebraic closure, you can check that this diagram is commutative on the set of elements, and this allows you to speak about equivalence of this notions of this one and given by the collection of elements. And notice that H, when you can speak about that H is defined over the field. Yeah, so this means that so you can sometimes put K where K is arbitrary field. So the equations that you are using this to define it as a closed defined varieties should have coefficients in K. Yeah, so if K is used in the notation, we mean that equations are defined over K. Yeah, so of course, the examples for this, so you may think of just a circle, yeah, just as x squared plus y squared equal to 1, or you may just put here so you can put in the coefficients somewhere you can put I, and so this will be as the variety. So this has coefficients that defines the circle and this group over R, but if you multiply by I, this will be the same set over C, but different subset over R. Yeah.
Could you say once again the two definitions of algebraic subgroup?
Yeah, so first of all, it should be a fine subvariety of G, and the second, you should have consistency with the group structure. One way to state it is to state that H is a subgroup of G, just said theoretically. Yeah?
This is so if it is so it's a theoretical, then both conditions hold.
Yeah, so if it is over K, so said theoretically, it is a subgroup of G over algebraic closure. Yeah, so that, I mean, if you think of its elements over the solution of the system of equations over algebraic closure, or you may speak about commutativity of this diagram. Yeah, so that the product is consistent.
So if H is a subgroup in a closed in an algebraically closed field, then the diagram is commutative.
Because it is commutative on a set theoretical, yeah, on the set of elements, and in order to define a subgroup, it is in maps. It is enough to check it on the set of.
It's just a statement like if two polynomials are equal as functions, they're equal.
Yes, yeah, yeah.
Even so that
Yeah, precisely. Можно по-русски спросить?
Мне немного непонятно, с какой стати, если H как подгруппа, сейчас.
Ну это знаю, если
Если H подгруппа, то тогда обязательно у нее будет регулярное отображение на умножение.
So if I mean, so this condition is both used here, yeah. So the question was, it is not clear why H is if H is a subgroup, there should be the map. But it if H is a so first of all, H is an algebraic subgroup. Yeah. So there is inclusion of H in G, which is closed embedding as a fine variety. Then you have you can write down this kind of commutative diagram, and so there are two options: to have this commutative diagram, or to have the subgroup of G as set theoretically. Set theoretically really means that this diagram holds set theoretically. But but over algebraic closure, to check this, if you already have these maps and you want to check the commutativity, which is enough to check it on the points, on the set of solutions. Yeah.
То есть если H это замкнутое афинное многообразие, то тогда мы можем говорить...
Ну, то тогда вы можете написать вот эти отображения, а единственное, что тут нужно, это проверить коммутативность этой диаграммы. Но она проверяется за счет того, что она выполнена теоретиком множественно, а это и говорит о том, что два отображения равны.
То есть все, что мы требуем на самом деле от алгебраической подгруппы, это выйти замкнутым афинным многообразием, а чтобы она подгруппой была, тоже требуем? Да, как теоретиком множественно, просто как бы умножение такое же, да. Получается, здесь нет никакой независимости,
да.
Только группа и замкнутая афинная многообразие.
Да.
And which map do we have in the product of subgroups to the...
What?
Which map do we have in...
This one?
Yes.
Yes, you should have the map. Yeah, so which is algebraic. Yeah, so this is this is closed variety plus algebraic group itself. But also, so there is consistency. So it is algebraic group plus. No.
So this mu is just.
But if you know this set theoretically, this mu is a restriction of the multiplication map. Yeah.
А бывает так, чтобы у алгебраической подгруппы была подгруппа, являющаяся замкнутым. Короче, чтобы была подгруппа алгебраической группы, которая сама не замкнута.
Да, конечно. Сейчас мы об этом поговорим. So here also I want to speak about actions. Да.
Если может ли такое быть, чтобы была замкнутая, чтобы была подгруппа замкнутое афинное многообразие, но чтобы умножение
не было согласовано, но это глупо. Такое бывает. Но...
Чтобы оно было согласовано на уровне
точек, но не так... Чтобы оно было не...
Нет, но оно как бы ограничение того отображения, что на G, просто как бы просто вы тут всегда делаете, как можно. Yeah, so the question is, so the next I want to define actions of algebraic groups on varieties, of algebraic groups on varieties. So here the situation is the same as in set theoretical context, except you add that now this is a regular map. So X should be algebraic variety. So for example, a fine algebraic variety. And here you should have, for the action you need the associativity of the actions, yes? So just that row 1 of G1, G2 applied to X, it is the same as composition of row of G2 applied to X and row of G1 applied to the image. So this can be expressed, and notice that G1, G2 is just, so here we are writing G1 to G2 as the product, yeah? So just mu of G1 and mu of G2. So this can be expressed as a commutative diagram that sends G times G to X. So there is a way to map it to by mu to G times X. Here you can apply rho, and this should be, so here you can apply here you can apply to G times X. We are applying identity map times rho here. So
in this case, you would write the top map like mu times.
Yes, to be consistent, and identity on X and identity on G. Yeah. So the claim. The usual action should be associative. So this is associativity for the action maps. So. Of course, this there are usual notions that are.
Once again, this question just for convenience. So, what is the same regular function? Is when like difference belong to ideal which describe G times X?
It's regular map. It's not function. I mean, it's collection of functions.
Yes, and two regular maps are same if each coordinate as polynomial belongs to ideal describing K times X in product, or how to think about it.
So the maps, if you think of affine varieties, so we can formulate these two maps are the same if they induce the same homomorphism between the pullback maps. So I mean, you can reformulate this as X times Y. So if you like, you may reformulate that pullback map are the same. So these are homomorphisms, and they are the same. Since for affine varieties you can reconstruct this, for general varieties we cannot reconstruct the even variety by the collection of regular functions. But this was definition for affine varieties. Here I actually didn't state what is algebraic varieties so far, but you should think of this as the part of machinery that.
So when you say diagram commutes, you mean these two maps
are the same.
Are the same map
of this variety to this variety.
But to variety, but not set to set.
It can happen that the map from sets are the same, but
so what is map of varieties in that case? It's map plus pullback.
Yes, I mean, so in order to, so here we have to define what is algebraic variety then. So algebraic variety, so here I would like to prefer to simplify it a little bit for the statement. So I assume that X is X is a topological space, so it is covered by the charts. So these are called charts, and these are affine varieties. So affine varieties. So if I want to glue the variety, I should specify what are the maps. So you should take intersections. So it is a subset in UI, and look at the image of this intersection as a subset of UJ. Yeah? So this is a phi ij map from the. So this is collection of the charts plus collections phi ij. So such that so we say that so we have the following condition that UI intersection with UJ are affine varieties themselves, so they can be put as a closed subset somewhere in some affine space. And also this phi j should be regular maps, regular isomorphisms. So phi j are regular isomorphisms.
Это должно быть, что в определении лаконной геометрии открытые подмножества, а здесь
Они открыты в пересечении, имеется в виду, что оно афинное, оно будет куда-то вложено в свое афинное пространство, но как замкнутое подмножество, то есть как... So there was some kind of confusion in the via the question, yes, so that here I'm speaking about, so in the usual topology, the intersection of two charts is open. So here, the intersection of two charts is also open, but I want to, so this is non-trivial condition, that I want to have the intersection of two charts to be possibly embedded in a affine space as a closed subset. Yeah, so like we have embedded the complement to zero of the line, we have embedded it as a closed subset somewhere. So I want to embed this intersection of these charts a priori to some affine space, possibly not related with UI UJ, or of some high dimension.
But this embedding is not like happening on picture below. I can't understand what F.
So here in this picture there is no disembedding.
Yeah.
But you have you have a map between this subset considered in UI and this subset considered in UJ. Yeah, so just
It's identity map. Is it identity map?
It is should be a regular and isomorphism, meaning that phi ji is also regular, and their composition are identity map.
Путаница возникла, что мы записали изначально x как объединение, как будто оно уже...
Да.
Вы как бы говорите, как склеивание.
Yeah, so just yeah, so you have disjoint union of charts that we want to glue. Yeah, so via identification. Yeah, so we want to glue via identifications. And X is just this disjoint union via this identification. So X will be the union of this, after the gluing, it will be the union of this chart. Ну, то есть, как бы мы делаем то же самое, что с любым многообразием, да, что у нас...
Вы про identification говорите, что оно регулярно, а регулярно оно может быть только в терминах того выражения.
Ну, регулярно, да, мы можем проговорить это только в терминах, ну, мы должны знать, что это афинное многообразие, ну, или так или иначе, как бы проговорить, что такое, ну, регулярное отображение в терминах афин. Ну, я просто сейчас не хочу говорить, что такое регулярное отображение для подмножества афинного пространства, но оно такое же определение. Да. Да, ну, то есть вот это нужно вложить куда-то в замкнутое. Ну, подмножество афинного пространства, и там это представить как многочлен. Yes, regular. So you should, there should exist an inverse one, which is also regular algebraic isomorphism, such that composition in both directions is identity. Yeah. So this is a definition of algebraic variety, and the definition of algebraic map of such varieties. So X is mapped into Y. So X is written as a union of charts. Yeah? Y is just written in the union of charts. And phi is given just via the following. So you just the image of phi is just covered by the so it is covered by the corresponding charts, and you may intersect the image with Vj. Yeah? So you can take preimage of UI and intersection with preimage. So this is set theoretic map such that intersection of UI and preimage of Vj is just isomorphism, is just a regular map. So the regular map on just in Vj. Yeah? So you should be able so better to say like this. So there exists some these algebraic varieties such that there exists a covering, so special the refinement of the covering for X such that preimage of Vj such that phi of UI sits only in one chart Vj, so the charts are sufficiently small, and the map, the restriction of the map on UI is a regular map of affine varieties. Map of affine varieties. So notice that regularity, so these are open subsets from the viewpoint of X and Y, but regularity is checked via embedding in affine space as a closed embedding. Yes, so these are open subsets.
So again, my question, this phi from X to Y has no additional data, it's just
so you have set theoretic map and a covering of X.
That proves that this phi is good.
Yes, yes. So that you restrict phi to this UI, and it maps. So this UI is inside the chart. Yeah?
And why this diagram computes when we are saying like about associativity, it was important.
А тут нет диаграммы.
No, I'm supposed to come back to diagram of associativity.
Да, ага.
Or group action.
Yes,
Anyway.
this one.
So yes, why we are saying that it's important to say that the diagram commutes in some category, but not like commutes in a row of sets.
This is, I mean, it is sufficient to check it again on the set of points, but if you...
In K equal K bar.
Yes.
And what is statements? So, what means diagram commutes without K equal K bar?
Ну, в смысле, что композиция этих двух отображений одинакова. Ну, что отображения одинаковые при композиции.
Two things that are equivalent when K equal K.
Yes.
First is set theoretically diagram commutes.
Yes.
And second?
And second, I mean that so you do not need to impose anything about set theoretical commutativity of diagram if rho is algebraic. I mean, rho and mu should be algebraic. Then, ну, rho должно быть морфизмом многообразий. Это, да, и диаграмма должна, должна быть коммутацией.
Два многочлена могут быть не равны, да, но при этом равны теоретиками.
Нет, имеется, ну, над алгебраическим замыканием такого, да.
Только алгебраическое замыкание.
Да.
Я не очень понимаю, где тут могут сравниваться два многочлена.
В смысле, когда вы сравниваете, so when you, there was a question about how to reduce the checking of that two regular maps are the same by comparing two polynomials, but they are done via the following. So x, if you are reducing it to the case of affine varieties, then you have a map. So x is embedded in an and y is embedded in am. Here you have a map, here you have the polynomials. So and here you compare the polynomials.
I can compare the polynomials and don't afraid that I will get unequal polynomials for equal functions.
Yes.
Okay.
Yeah.
Thanks.
Okay, great.
Definition of algebraic variety, you mean finite encoding?
What?
Finite encoding by affines.
Usually yes. Yeah. I mean, just in a conventional setting, yes, but sometimes if you want something, you can generalize it, but... And also, yeah, so here you should say that, of course, if you have such coverings, it's an X, so X, if X is written in terms of charts, yeah, so U is called the risky open, if and only if U intersection with UI is open in UI. Yeah, so for affine varieties we have a notion of the risky openness and closedness, and so you have the same criterion closed. So the same criterion for checking that the subset is open or closed. Yeah, so just let me just Z in X is closed, is the risky closed, if and only if the intersection of Z and UI is closed in UI. So that's why we are, so we wanted to start at least with affine varieties, affine coverings, where we know these notions. Что, уже пора заканчивать? Ага. Ну, давайте тогда все на сегодня. Спасибо.
Спасибо.